This video is going to discuss some special limits of trig functions and how we can use them to evaluate other trig limits. So I have two special limits on the screen. The limit as x goes to 0 of sine x over x is equal to 1. And I have a proof of that limit in the squeeze theorem video. If you're interested, take a look at that. And then the limit as x goes to 0 of 1 minus cosine x divided by x is 0. We're going to start with these two special limits. And again, I'm not going to prove them here. I have the first one shown in more detail in the squeeze theorem video. But what we're going to do in this video is just use these special limits as a starting point to find other limits. And let me show you what I mean by that with an example. Let's see if we can find the limit as x goes to 0 of sine of 4x divided by x. If I plug the x value in, I'm going to get sine of 0, which is 0, divided by 0. I'm going to get 0 over 0, which is one of my indeterminate forms. And so my goal with this problem is to somehow manipulate this problem. So I have something of the form limit as theta goes to 0, sine theta over theta, because I know that limit equals 1. So I'm going to try to manipulate this problem so it looks like the limit that I already know. And so notice that the limit that we know, this sine theta over theta, as theta goes to 0, the angle and the denominator are the same. So if the angle and the denominator are the same, the limit goes to 1. In my problem, I have limit as x goes to 0 of sine of 4x over x. I have a 4x as my angle, so I really want the denominator to also be a 4x. So what I'm going to do is multiply both the top and bottom by 4. I have to multiply both the top and bottom by 4 because I don't want to actually change the value of this expression. I want to make sure I'm doing the same thing to the top and the bottom. So now I've got limit as x goes to 0 of sine of 4x times 4, and then I'm just going to write the denominator as 4x. So again, I've got limit as x goes to 0 of sine of 4x over 4x times 4. I can find the limit of each of these pieces separately. This is a product. When we have a limit of a product, we can rewrite that as a product of limits. And the limit as x goes to 0 of sine of 4x over x, that's going to equal 1 using the property we just learned. Anytime your angle and your denominator are the same, that limit as the angle goes to 0 is going to equal 1. So if theta is 4x, for example, I do have something of the form sine of theta over theta. That's going to go to 1. And then the limit of my constant 4 is just 4. And so my final answer would be 1 times 4, or 4. Let's see how this works with another example. I've got limit as x goes to 0, tangent x divided by x. Again, if I just plug the x value in, I'm going to get something that's indeterminate. I'm going to get 0 over 0. So instead, I'm going to start by just replacing my tangent x with sine x over cosine x. So this problem becomes limit as x goes to 0, sine x over cosine x divided by x. Dividing by x is the same thing as multiplying by 1 over x. And then, because when we multiply, the order of multiplication doesn't matter, I'm just going to switch the x and the cosine x and rewrite this as limit as x goes to 0 of sine x over x times 1 over cosine x. And the reason I did this is because now I have that sine x over x. That's my common limit that I have memorized. So now we're finding limit as x goes to 0 of sine x over x. That is just 1 times the limit as x goes to 0 of 1 over cosine x. And for 1 over cosine x, I can just plug in the 0. 1 over cosine 0 is just 1. 1 times 1 is 1. Here's another one. Limit as x goes to 0, sine of 5x divided by 7x. If I want to take advantage of that special limit, I need to have something of the form sine of an angle divided by the angle. So I'm going to start by looking at my numerator. My numerator is sine of 5x. And so it'd be really nice if there was a 5x in the denominator, because then I could have a sine of 5x divided by 5x. So I'm going to multiply both the top and bottom by 5x. Again, always doing the same thing to the top and the bottom, so that we're technically multiplying by 1 and not actually changing the value of our expression. Then, notice we have a sine of 7x in the denominator. It would be really nice if this 7x, sine of 7x, had a 7x on the other side of the fraction bar. So I'm just going to go ahead and multiply the top and bottom by 7. And now let's see if we can rearrange things to get those special patterns that we're looking for. And again, we have a bunch of multiplication. The order of multiplication doesn't matter, so I can change the order of some of these pieces in my product. And so I'm going to start by grouping the sine of a 5x divided by 5x together. So I've got sine of 5x divided by 5x. And then I want to group my sine of 7x with a 7x. And so I'm going to do times 7x and then sine of 7x in the denominator. And then finally, what are we left with? We're left with a 5 and a divided by 7. And so now I'm going to try to find the limit as x goes to 0 of sine of 5x over 5x times 7x over sine of 7x times 5 over 7. So this first piece, limit as x goes to 0 of sine of 5x over 5x, that's my special limit. That's just going to equal 1. The second piece, 7x divided by sine of 7x, that's actually the reciprocal of sine of 7x over 7x. And we know what the limit of sine of 7x over 7x is. That's also going to be 1. And then I'm left with 5/7, which is a constant. And if I take the limit of 5/7, I get 5/7. So final answer here, we're going to get 1 times 5/7. My final answer is 5/7. All right, that was my last example in this video. Let me know if anything is unclear.